All right. So of course the test is today after class, so it will come on at 1:15, and just when the class ends, right? And then it's just the usual procedure. So you will write your answers either on, you can print the test or on a separate sheet of paper, and then you will scan that to PDF, and then you will of course email that back to me. And since this will overlap another class period, the Thursday class period, the due date is Thursday at 5 p.m. Okay, so it will be due Thursday at 5 p.m. That's when you need to submit it, or of course you can submit it before that, right? So, but that's the final time to submit. So you just email me back to my usual email address, which is wallerw@uhd.edu, and that's on the test. So just like last time. So all that should by this time should be quite familiar to you. One thing that I wanted to warn you about on this one is be sure you be careful to show your work, right? Where work is required. So that's going to be really important on this test. So try to write down steps to solutions to problems, or steps to, when you're differentiating functions and so forth. Make sure that you include steps. Don't just write the answer down unless it's something that's just a very simple question that doesn't really require any computation. So if it's something so easy that it doesn't require any steps, that's one thing. But if it's something that's a little bit more complicated and obviously does require some work, be sure you include those steps. Now that doesn't mean you have to write down every single painstaking detail, but you have to write down enough, as I say on the test, to justify your answer, right? So that's really important on this test. I'm going to be looking for that, especially on differentiation problems. I need to see some of the steps in the differentiation as we have been doing them in class, as I have taught them in class, right? So if you have differentiation steps that I know are something that I didn't show you, okay, and that you would not normally see or not normally do, I'm going to suspect that that was computer generated. So I don't want computer generated answers, right? Okay, this is your work, right? So make sure that you're doing the work, right? Not relying on your calculator, for instance, right? So, and I can very easily detect calculator generated answers. So just a warning there, okay, about how I'm going to grade the test. Okay, so be careful about that. So implicit differentiation was due at I originally had it set at 11:30 today. I just wanted to try to get you to finish that before you started the test, but I moved it back to midnight. Since you're usually more accustomed to having things due at midnight. So I did move it back to midnight, so you have more time to finish this one, but that is overlapping with the test, right? So, but anyway, so I did move that back slightly. Do y'all have some questions for me on anything? There are a couple of problems on the implicit differentiation I wanted to look at that were being flagged as people were maybe missing those. They're a little bit trickier problems, so I will call those up. But do y'all have any questions in particular that y'all want to ask about, either on this homework or on something else? Okay, no. So I'm assuming then that y'all are comfortable with. I'm assuming you're comfortable with your preparation for the test. So so that's great. Let's all right, let me I'm not even going to open this this implicit differentiation homework, because I already wrote down the questions that I wanted to look at. So we're talking about limits. Before I look at that, intro to limits. So we did this last time, and that's due on Saturday. So I moved that back to Saturday. And then we'll talk more about evaluating limits today. Actually, we'll make it a little bit easier than we started with today. And then there's another homework on that, which is due actually not till next Tuesday. Okay, so I was trying to move those back out of the way so you'll have time to, between now and Thursday, to do your homework. I'm sorry, to do your test, right? Okay, let me see if I can find this these problems that I wrote down, and from implicit differentiation, and this will just give you a couple more examples to help you prior to opening that test. I think I wrote them down here all the way somewhere here at the bottom. Here they are. All right. So I think these are the numbers on these were 7 and 8 on that homework, but your number, the constants that are in your version of the problem when you open your homework may be different than these. These were what it was showing to me when I opened them. But it's going to be very similar. So this first problem, number 7, was, I think it wanted you to find the equation for the tangent line of this curve. I think this is a parabola when you graph it, but it's a parabola that opens to the left or the right, not up or down. But anyway, no matter what the curve is, we wanted to find the equation for the tangent line at this point. So apparently this point 6, 5 is on the curve. Is that correct? 6, 5 is on the curve. Yeah, that's right. That point is on the curve, and so we just want to find the equation for the tangent line to the curve at this particular point. So of course, tangent lines, right? That means you need to find the derivative, and then use the derivative, right, to find the slope of the curve at this particular point, and then of course, once you know the slope of the curve at this point, and you have this point, then you can easily write down the equation for the tangent line, right? So we just have to differentiate this equation. And so we're going to use implicit differentiation to differentiate this. And I think probably what maybe threw people off was differentiating the left-hand side here. The right-hand side is pretty easy to differentiate. Remember, implicit differentiation, you're going to differentiate both sides of the equation. Remember, you're differentiating with respect to x, right? Because at the end here, we want to find the derivative of y with respect to x, dy over dx, which you can also label as y prime, recall. So since the right-hand side here only involves the variable x, this is really easy to differentiate with respect to x. This is just like differentiating this function. I'm going to multiply the 4 times the x minus 5. So we have 4x minus 20. So this is just like differentiating 4x minus 20, right, in the standard way. And so when you differentiate that, you would get just 4, correct? Because the derivative of 20 is 0, and the derivative of 4x is going to be 4. Okay, so that's very easy to differentiate. What's trickier to differentiate is the left-hand side, because remember, you're differentiating with respect to x, correct? But the left-hand side contains the variable y. All right, so here's the way you do this. It's actually easy. It's just a matter of thinking about it correctly. You're going to use the power rule here. So you're because you have a power, right? Okay, this power squared. So you'll just start off using the power rule, just like you normally would, right? So you bring the 2 down. So you have 2 times y minus 3 to the 2 minus 1, which is 1. So you get 2 times y minus 3. But remember, you're raising an expression to a power, right? And so the chain rule comes into play here because you have the expression y minus 3 that you're raising to this power. So you have to multiply in the derivative of y minus 3, okay, on the left-hand side. Well, let's see if we can find the derivative of y minus 3. Remember, with respect to x. Well, the derivative of 3 is 0, so that's not going to make any difference. But what's the derivative of y? Remember, that's what we're trying to find here, is the derivative of y with respect to x. We don't know that yet, right? So for the time being, we're just going to write down, okay, I got to multiply in the derivative of y. So we'll just call it y prime. That's its name, right? We don't know what its expression is yet, but we'll just write down this variable to represent the derivative of y with respect to x, right? So we'll write in here y prime. So that's the derivative of the left-hand side. It's 2 times y minus 3 times y prime. Okay, it's just like if you were trying to find the derivative of x minus 3, x minus 5 to the 10th power, right? How would you find the derivative of that? You would bring the 10 down. Let me change this. Suppose it were 2x minus 5 to the 10th power. How would you find the derivative of this? You would bring the 10 down, right? Okay, and then times 2x minus 5 to the 9th power. But then you have to remember to multiply in the derivative of 2x minus 5, which is 2. Okay, that's exactly the same thing that's happening here. Bring the 2 down times y minus 3, but then you have to remember to multiply in the derivative of y minus 3. Unfortunately, you don't know what the derivative of y minus 3 is, so you just have to fill in y prime, okay? Now, we're going to soon find out what y prime is, right? Because we're going to solve this equation now, not this equation. We're going to solve this equation for y prime, right? So the derivative of 4x minus 5 is 4. The derivative of the left-hand side is this. And now how do we solve this for y prime? Oh, so easy. Just divide both sides by 2 times y minus 3, right? And you'll just get y prime left on the left-hand side. So you get y prime is equal to 4 over 2 times y minus 3. I guess you can divide the 2 into the 4, and you get 2 there. So you end up with 2 over y minus 3. See how nice that is? Okay. So that's it. There's your expression for y prime. That's interesting. Notice that expression doesn't even have an x in it. I guess it's not necessary. Okay. All right. Now, we wanted to find, though, that was only part of the problem, right? We wanted to find the equation for the tangent line at this point, 6, 5. Okay. So we need to know the slope of the tangent line at 6, 5, right? Well, let's see. You use the derivative to find the slope. And the derivative says, okay, the slope is going to be 2 over whatever your y-coordinate is of this point minus 3. Notice the x-coordinate doesn't, in this case, doesn't turn out to have any impact. So in other words, you're just going to evaluate y prime at 5 because x is not in this formula at all. And that turns out to be what? 2 over 5 minus 3, which is just 1. So we get a really nice, pretty derivative at this point. The derivative is 1. And so that means the slope of the tangent line is 1. So what's the equation for the tangent line going to be? Well, let's see. It's going to be y equals 1, which is the slope, times x minus the x-coordinate of this point, which is 6, and then plus the y-coordinate of the point. So you end up with, that's it, okay? I guess you could simplify that, but really don't have to, okay? All right, so you probably have a problem similar to this, right? Where you've got some curve and you want to find, or you're given the implicit derivative of that curve, and then you want to write down the equation or the slope for the tangent line at a particular point. So here's a good example of doing that. Now, this question, the next question also was hard for people. Okay, so this one is terrible because the numbers are so large. All right, so they gave you this curve, 81x squared plus 16y squared plus 648 times x minus 288 times y plus 1296. Your version of the problem probably had different coefficients here. Okay, but anyway, so you had an equation like this one, and I think what you were asked for is where does this curve, when you graph it, where does this curve have horizontal and vertical tangents? Okay, So where is the tangent line going to be horizontal? And where is the tangent line going to be vertical? So horizontal tangent lines, of course, have slope 0. What about vertical tangent lines? What is their slope? Someone? So if you have a vertical tangent line,
Undefined.
What's the slope of a vertical line? So
Undefined.
Colin, what's the slope of a vertical line?
Sorry, undefined.
Undefined, right? Okay. So so we need to keep that in mind, right? Okay, we want to know where does the tangent line have slope 0, and where does the tangent line have undefined slope? In other words, it's going to be vertical. Well, to find slopes of tangent lines, right, you're going to have to find the derivative of this curve. And actually, when you graph this curve, it turns out to be an ellipse. If you graph this curve, you'll get an ellipse. I didn't draw a graph of this, but that's what that equation results in when you graph it. So obviously, we're going to do implicit differentiation right here to get an expression for dy over dx or y prime. So that we can investigate where the tangent line is going to be horizontal or where it's going to be vertical. So let's do the implicit differentiation. So that's easy for the right-hand side because the derivative of 0 is 0, right? Okay, so that's no work at all. A little bit of work now here on the left-hand side, right? So let's just go term by term and differentiate all of these terms. Remember, with respect to x. So this expression just involves x anyway. So differentiate this is easy. It's just the power rule. You'll bring the 2 down and multiply it by the 81. So I guess you get 162 times x. Don't let me mess up the arithmetic here. 2 times 81 is 162, right? Now, this one's trickier because it involves the variable y, but you're still going to use the power rule. So you bring the 2 down. That gives you 32. 2 times 16 is 32. Times y to the first power, right? Because subtract 1 from the exponent. But remember now you have to multiply in y prime, okay? That is the chain rule. What's the derivative of 648 times x? That's easy. That's just 648, right? What's the derivative of 288 times y? Well, that's just 288 times the derivative of y, which is, we just have to call it y prime because we don't know what y prime is yet, right? And then what's the derivative of 1296? That's a constant, so its derivative is 0. Oh, nice. So it's not looking too bad, right? Now you're going to rearrange terms, right? You're going to keep the y prime terms on one side, and the other terms you're going to move to the other side. So on the left-hand side, I'll keep 32 times y prime minus 288 times y prime equals, and then move this term and this term to the right-hand side. So I have minus 162 times x minus 648. Remember, we're trying to solve for y prime now. So factor y prime out of the left-hand side. So you get y prime times 32y minus 288 equals all of this. And now divide by the 32y minus 288, right, on both sides. So divide this out, and it's not negative 32, it's just 32 y minus 288 on both sides. So it looks like there's your expression for y prime. All right, so see, that's the derivative now we can use to figure out where the tangent lines are going to be vertical and where the tangent lines are going to be horizontal, right? Okay, now how is it that we do that? Well, again, we said horizontal tangent lines have slope 0, right? So we're figuring out what x and y values will make this derivative equal to 0. That is where we're going to have horizontal tangent lines. So you're taking this fraction and setting it to 0 and solving it. Now you have to remember, when is a fraction equal 0? It's only equal 0 when the top is 0, right? So really the equation you're solving here is minus 162x minus 648 is equal to 0. But that's a pretty easy equation to solve, I think, I hope. So that's minus 162x equal 648. And does that work out nicely? If you divide by minus 162, does that come out to be a whole number? I think it does. Doesn't it come out to be minus 4? Isn't that minus 4? If I'm
yes, minus 4.
Oh, good. Oh, we're lucky, man. I was afraid it was going to come out to be some weird fraction. But it's just minus 4. So you know that when x is minus 4, right, that is where you're going to have horizontal tangents. Now, you want to know the actual points where the tangents are horizontal. So you know the x coordinates are minus 4. Okay, so the points on the curve where the x is minus 4, that is where you're going to have a horizontal tangent. But the y coordinate is what you need to know. So what you have to do is take the minus 4 and plug it back into the original equation for x. So you have to come back up here and plug in minus 4 for x. And what's going to happen when you plug in minus 4 for x is you're going to end up with an equation that just has the variable y in it. So you'll have some equation here with y's in it equals 0. And so solve that equation for y. Okay, it's going to end up being a quadratic equation because notice that you have y squared here, right? And so you have to solve that equation for y. And I think you'll end up with 2 y values here. Probably, well, you're going to end up with 2 y values here, okay? So I'm not going to go through that process because that's just a matter of solving a quadratic equation. So plug in the minus 4 for x. It's going to the arithmetic is going to be a little bit messy because you've got large numbers here. But plug minus 4 in for x, you'll end up with an equation that just has y in it. Solve that equation for y, and that will give you the 2, I think it's 2 y coordinates here. So you'll end up with 2 points. Both of them have x coordinate minus 4, but 2 different y coordinates, okay? So those 2 places, the tangent line is going to be horizontal. Now, what about where it's vertical? So what do we say about vertical lines? What's their slope?
Undefined.
Undefined. So the question you're asking yourself here is, where can I make this, where is this fraction going to be undefined? Not 0, but where is it going to be undefined? Okay, well, when does a fraction turn out to be undefined?
The bottom equals 0.
The bottom equals 0, right? You cannot divide by 0, right? So if the bottom of it, I'm sorry, not 0, we already did that. But we want this fraction to be undefined, right? Okay, so that's going to happen when the bottom is 0. So now take the bottom and set that equal to 0 and solve that equation. And you'll end up with y equals, this is 9, right? So you end up with 9. So these points where x is minus 4, you get horizontal tangents, but the points where y is 9, don't know what the x coordinates are, but the points where the y is 9, those are going to have vertical tangents. So you do the same thing. Take the y value 9, plug it back into this equation, and that will leave you an equation that just involves x. Solve that equation for x, and you'll get the 2, I think there are 2 of them. So you get two x coordinates here where you have vertical tangent lines. All right. So get the idea there. Okay. So that solution takes a page, Madison. So already in calculus, right? We have a long we have a long problem with lots of steps to it, right? To get the solution. So you guys have all the basic knowledge, right, of these sorts of questions, because they all involve usually taking the derivative and setting it to 0, or evaluating the derivative to find a slope, right, for a tangent line. That's really such a big part of differential calculus, right? Just recalling, right, that derivatives and slopes of tangent lines are the same thing, right? Or rates of change, derivatives, and slopes of tangent lines, those all are just interchangeable terms, okay? All right, so, well, there's a couple of questions from implicit differentiation. I don't think anything on the test is involved as that, however, okay, as that homework problem. So I hope you find that reassuring.
Hey, Professor, I had a question.
Other questions? Yeah, Lance.
So, so for this question number 8, could the answer just be 9? Or did you want it to where it was like both?
I think it wanted, I think for WebAssigns, it wanted the points. It wanted the coordinates of the points, Lance. So,
yeah, both.
So you have to find this x coordinate also that goes with the 9, and to find that you have to plug the 9 in. The same thing here. It wanted the y coordinate that goes with this x value -4, so you had to plug the -4 in and solve an equation.
Okay.
Yeah, I think so. You end up with that. That's why you have all this extra work.
Like it wouldn't just be -4 and 9, because okay, I got you.
Oh no, yeah, no, negative. If you put 9 here, I don't think, maybe, but I don't think that point is actually on the curve.
Okay.
Yeah. Okay. I'm not sure what the y for this curve. I'm not sure what the y value is that matches -4. That's why we have to plug the -4 in for x and solve for y. Okay. I think it comes out to be a whole number, though. It doesn't come out to be some unusual, square root or something. Yeah.
Okay, thank you.
Okay. All right. Okay. So other questions there before we talk a little bit more about limits?
I have just a quick question
Uh-huh.
about
Yeah.
like the writing format in the test. So
Mhm.
for example, if like this specific problems is in the test,
Mhm.
would you refer us to show you all the calculation when we like replace the x and the y in, and then solve the quadratic one with like quadratic formula and all of that?
Yeah, you would have to write down maybe not every single detail, but you would have to write down a good part of that, right? It would have to be clear to me what you were doing.
Okay, so
Yeah.
we need to replace them twice for each, like for the x and the y, and then show you all the calculation for
Yeah,
the
you would,
points.
you would replace that. You may not, so you might, show the x, for instance, show the x being put in, and then show the equation that you get, and then maybe you don't have to show every step of solving the equation, but have to be clear that, oh, that person is solving this equation, right? And that's how they're going to come up with the y values.
Okay, got it. Thank you.
But solving a quadratic equation is that requires a few steps, and you're gonna have to write those down somewhere. So just write them down on the test. Okay.
Yeah, because I was just asking just in case, like because it's like we got ugly numbers or something, so it's gonna like take a while.
I hope the numbers aren't too ugly.
Oh, okay, got it.
I don't know. I haven't worked through all the problems on the test, so I don't know. I hope they're not. Okay. All right. Okay, so let's look now at continue with limits, and we're going to get a break here now. So let me. Oh, it's the same notes. So let me scroll back up to the top. So remember, we said sometimes evaluating limits can be tricky because you cannot just substitute the limit value into the expression to determine what the limit actually is. Okay, and because sometimes when you substitute the limit value into the expression, you end up getting dividing by 0 or some situation like that. Okay, and so that makes it sometimes complicated to figure out what the limit actually is. So, but we're gonna we end up here getting it turns out we get a lucky break though. Okay, in many instances, evaluating limits will actually be straightforward. You can evaluate the limit just by substituting the limit value into the expression that you're trying to take the limit of. Okay, and that comes about as a consequence of continuous functions. So this is one place where continuous functions are going to be really helpful to us. So remember in calculus, so we've said this now several times, in calculus we have these sort of three big features of functions that are really important to us: the direction of the function, whether the function is increasing or decreasing. And so we've talked about that a lot. That's what the derivative really helps us understand. Where a function is increasing or decreasing, and where it's, in particular, where it switches from increasing to decreasing or decreasing to increase, because that's where you have a turning point, and turning points are where you're going to have, a relative maximum or a relative minimum, which are those are important points to us on a function because they usually help us answer practical questions. And then there's curvature of the graph, right? That's also known as concavity, right? So that's the shape of the curve, right? Concave down, right, like this, or concave up. Okay, so that's another important function feature that we study in calculus. And then the other third one is continuity, right? Whether when you graph a curve, whether it's unbroken or not, right? Okay, and but our definition of continuity up until now has been very informal. We said a function is continuous, right? Or it's if it's unbroken. But limits actually give us an opportunity now to write down a more rigorous, formal mathematical definition of what continuity actually means. Okay, instead of just using this very informal term, a function is continuous if it doesn't have a break in, or if it doesn't have a gap in it, right? Okay, those are kind of very informal and vague terms. They're not mathematically precise. But this idea of limits, or computing limits, gives us a method of writing down a precise definition of continuity. Okay, and so let me show you this. Let me show you this mathematically correct, a rigorous definition of a continuity. Okay, so we say a function is continuous at a number, say x equals c. So c can be just some constant, right, that we choose. So a function is continuous at some x value if the following three things are true. Okay, so first, the function has to be defined at that number. So if the number c is not in the domain of the function, then there's no way the function can be continuous at the number c, right? Okay, if you think of that geometrically, if the function is not defined at an x value, that means the graph does not exist, right, at that x value. So obviously you must have a break in the graph at that value. Okay, so you can't have the function be continuous. So first, the function has to be defined at this whatever number you're interested in. Okay, all right. Next, the limit at that a value of the function has to exist. Okay, so the limit as x approaches c of f of x, that limit must exist. It cannot be, by the way, plus or negative infinity. Okay, sometimes we talk about limits being positive infinity, or sometimes we talk about limits being negative infinity, but for the purposes of continuity, the limit must exist, and it cannot be plus or minus infinity. It has to be a finite number. Okay, so this limit has to exist. And then finally, and it's the third thing that's really the key here, the limit and the function value have to match, okay? So if the function is defined, that's kind of a given, has to be defined to be continuous. If the limit exists and the limit and the function value at that number c match up, then the function is continuous at that number c. Let me show you an example of not being continuous, and you'll get an idea of why these three conditions are necessary to get a continuous function. So look at this graph that I just made up. Okay, so let's call this, let's say this is our function f. And we want to know, is the function f continuous at this number c? Okay, so we're just focusing on this x value c. Now, you can answer by looking at the graph, you can immediately answer this question. Is the function f continuous at x equals c? Is it yes or no? Just from your informal knowledge of
No.
It's no, right, Colin? Because obviously what's wrong there?
It's not on the major line. It's just
Yeah, what do you have in the graph that makes it not continuous there?
Oh, like which one of the choices, 1, 2, or 3?
No, just informally, what's wrong with the graph?
Well, that C point.
Yeah, that C point. Yeah, what's wrong at this?
Floating out in the middle of nowhere.
It's floating out in the middle of nowhere, and and it's causing you to have what in the graph there?
Oh, a discontinuity?
Yeah, okay. Well, you're saying it very carefully. I was expecting you to say something like a hole in the graph or a break in the graph, right? Okay. Yeah, obviously right here you have a break in the graph, correct? Right? Okay. Because of this, just the weird quirk that at C, notice the output here drops down, right? Okay. So you have a hole in the graph or a gap in the graph, or however you want to inform, a break in the graph, however you want to informally say that, and that causes it to not be continuous there, right? So you can see that very clearly from the graph. All right. So if I ask you, is this a function continuous at x equals c, you can immediately say no, right? Okay. I mean, intuitively you can see that it's not, Colin. But what's harder, if I ask you, well, formally, why is it not continuous? So which of these conditions is not met? Okay, that's let's see if we can answer
3.
that. Okay, so what'd you say immediately there?
3.
3. Yeah, 3 is wrong. Now let's see why it's not the first two. First, f of c has to be defined, right? Is f of c defined? Yeah, sure, right there. It's right here, correct? Whatever this number is, that is f of c. So yes, the function is defined at x equals c, right? Okay, c is part of the domain of the function. All right, so this one checks off easily. So that's not a problem. Okay, so that's not preventing it from being continuous there. Now you might think, okay, this is what is wrong. All right, the limit as x approaches c does not exist. Okay, but Colin, the limit as x approaches c does exist. What is the limit here for this graph? Let's see, as x approaches c, what's happening to our curve? What's it going up to? On both sides, what's it going up to? What value?
B.
B, right. So this limit does exist. It's B. Okay. So 2 is okay because the limit exists. All right. But you are right, Colin. All right. What's wrong is the limit and the function value don't match, right? Okay. That is why this is not continuous, because we said the limit here is B, right? But what's f of c? I'm
Something
not
like
sure.
Half B.
What now? What?
Half B? 1/2 B?
Yeah,
Something?
it's something like 1/2 B, right? Okay, or it's certainly less than B, right? So so these two things don't match up, right? I didn't write that right. It's less than B, right? Okay, so clearly, right, the limit and the function value do not match one another. So that one doesn't work. So not continuous. Okay. So if you combine these three things, that gives us a formal definition of when a function is continuous at a point. Okay. Now, just like us, mathematicians understood the idea of continuity informally long before they were able to write down these three conditions. Okay, so the notion of continuous functions has been around a lot longer than these three formal conditions for continuity were known. All right, let's take a look at another example, and y'all can help me understand. So we've seen y'all can help me understand continuity better. So we've seen this graph before. This is a function called a. Just made that up. All right, so this is a function called a of x. So it has a really weird graph, right? Okay, so in practice, you're not likely to run across a function with a graph as weird as this one. So this is just made up, right, for our purposes. So where is this? Our question is, where is a not continuous? And again, you can figure that out easily just from looking at the graph, right? So it's not continuous at, let's see, where would it be? So where do we have breaks or holes in this? Where do we have breaks or holes in this picture?
-3 and 3.
What's that look like?
And -7.
That's -7, right? So clearly at -7, not going to be continuous, right? Because we've got this vertical asymptote right there at -7, right? So not continuous there, right? Okay. And then where else now? What's the next one? As we're going from left to right here.
-3.
What?
-3.
Yeah, -3, clearly, right? You've got a break here at -3, correct? Okay, so -3, and then where's the next one? Right here, right? Okay, so that is 3. So not continuous at 3, and then where's the next one? Right there. I forgot what number that is. What, 6, 7, 8, 9? So not continuous at 9, right? Because again, you've got this vertical asymptote there, right? Okay. So so let's go back and just quickly explore from the definition. So we can easily see from the graph, right, where it's not continuous. So it's not hard to answer that question from looking at the graph. But let's see if we can figure out the formal reason why why this function a is not continuous at these numbers. All right. So which of these three conditions does this function a violate so that it misses being continuous? So what about there at -7? What's the problem at -7 that keeps it from being continuous there? So which of these conditions does it violate?
Is it 1?
It's 1. Yeah, you're right, Colin, because it's 1. Because what about a of -7?
It's some vague number between those two lines.
Yeah, it doesn't exist. All right. So a of -7 is undefined. Okay. A of -7 is undefined because you have this vertical asymptote here. Okay. So that indicates that the curve doesn't cross over that vertical asymptote. That means there is no value a of -7. All right. So not continuous because the curve doesn't even exist here at -7. Okay, it completely skips over that x value. All right, so it's number 1. A of -7 is undefined. Okay, that's exactly what happens also here at 9, right? Okay, a of 9 is because you have another vertical asymptote. Right, so a of 9 also is undefined, and so that keeps it from being continuous there at 9. So problem there. What happens now in what happens now at -3? Okay, so what's the problem at -3? Which one of those conditions is missed there? Can y'all tell that? It is defined, okay, so the function is defined at -3 because there's the output value. A of -3 is 2, right? Okay, so A of -3 is 2, so you definitely have an output there at -3. So so number 1 is okay. The function is defined at -3. -3 is part of the domain. But what is wrong here? Which one is missed? It's number
Can't
2.
tell if it's 2 or 3.
Yeah, well, it's once it's 2, then 3 is already violated. Okay.
Okay.
So
Good.
yeah, so it's number 2. All right. The limit does not exist at -3. Now, why doesn't the limit exist at -3? Because look, if you take the limit from the left-hand side, what's the limit from the left-hand side here? As you're moving from the left up to -3 on the x-axis, what's the curve going to? It's going to 5, right? But as you come from this direction to -3, what's the curve going down to? 2, correct? So notice that you've got the curve is approaching different values from the left and the right. And that means you don't have a limit, okay? The limit from the left and the limit from the right do not agree. From the left, it's 5. From the right, it's 2. So that means there is no limit. So number 2 is violated. You don't have a limit here at x equals -3. When the limit doesn't exist, that like in this case, that means you're going to have a break in the graph, just like we have here. You're going to have a break in the graph, and so you're going to have a discontinuity, right? Okay. Now, here's the case that we saw above, right? So what's the problem here? The limit exists because as you come up to 3 from the right-hand side, the curve is going to 4. And as you come up to 3 from the left-hand side, the curve is still going to 4. So the limit exists, okay? So actually the limit as x goes to 3 of this function a, that exists. It happens to be 4, okay? Both directions, as you move toward x equal 3, the curve is going up to 4. But unfortunately, what is a of 3? So what's the actual function value at 3?
2.
It's down here at 2, right? And so guess what? The limit and the function value don't agree. The limit is 4 and the function value is 2. So that's a second situation that gives you, you're going to have a break in the graph there, right? Okay. The curve is going up to 4, but the actual function value here is down at 2. So you get this weird hole in the graph, right? Okay. And that is a discontinuity. So we can use the idea of limits to give us a formal definition of when a function is continuous at a particular number and when it's not continuous. Now, let me show you how that's going to be useful to us in evaluating limits, because it turns out in the class, as you probably already noticed, we don't deal with functions like this very often in the class, right? They're just kind of contrived examples. In the class, most of the functions that we're dealing with are continuous functions, okay, right? In fact, we've almost exclusively dealing with continuous functions. So polynomials are continuous functions. Rational functions, that's quotient of polynomials, they're going to be continuous functions, at least where they're defined. They're going to be continuous functions. Trig functions are continuous functions. All right, at least for the values that are in their domain, they're going to be continuous functions. So a lot of the functions in our class are either continuous everywhere for all real numbers, or at least they're continuous everywhere where the function is defined. And so that's going to make it easy for us. that's going to help us in evaluating limits, as it turns out. Okay, helps us in a lot of ways, but in particular, it's going to help us with evaluating limits. Let me show you a quick example here, and then we'll take a break. So suppose we want to evaluate this limit of this expression. Pretty easy expression there, right? 4x squared plus 3. And we want to know what's the limit of this expression as x approaches 2. So what value is this expression getting close to as x approaches 2? All right, so let me think of this expression here, 4x squared plus 3. Let's think of that as the formula for a function. All right, let's call that function f of x. So we're going to let f of x be, in this example, 4x squared plus 3. So in other words, I'm just trying to find the limit as x approaches 2 of f of x, where f of x is 4x squared plus 3. But what do you notice about this function 4x squared plus 3? That is a polynomial function. In fact, it's just a quadratic function. It's just x squared, right? So that's a quadratic function. And as I mentioned above, polynomial functions are continuous functions, okay? That's one of the nice things about polynomial functions is they're continuous functions. So they're going to be continuous everywhere in their domain, everywhere where the function is defined. But for polynomial functions, that's all real numbers. So this function is going to be continuous for all real numbers. In particular, it's going to be continuous at x equals 2. So guess what that means? That means that the limit as x approaches 2 of 4x squared plus 3, f of x, because this function is continuous, that has to be the same as f of 2, right? Because that's one of the necessary conditions for a function to be continuous. Its limit at a number has to be the same as the function output at that number. But what's f of 2? Well, that's easy to calculate, right? Just take 2 and plug it in for x into this formula. And when we do that, what do we get there? Well, you get 4 times 2 squared. So that's 4 times 4 is 16, right? So 4 times 2 squared plus 3, 16 plus 3 is 19. So look, without any work at all, or without having to draw a graph, we figured out what this limit is going to be. It's got to be 19, because we know this is a continuous function because it's a polynomial function. So, so to evaluate this limit, all I have to do is, I don't have to draw a graph, or I don't have to do anything fancy. All I have to do is just take the 2 and plug it into the expression for x, and you get 19, and there it is. There's the limit. Okay, so it's the easiest possible limit you could compute, right? You just calculate that limit by substituting 2 in for x. So when we're computing limits and we realize that the expression that we're trying to calculate the limit for, if we realize that's going to be a continuous function like this one, then the limit's going to be really easy to compute. All you have to do is plug your limit value into your expression, do the calculation, and that's it. There's the limit. So you don't have to do anything special. You don't have to draw a graph and try to figure out the limit. You just have to substitute the limit value into the expression and do the arithmetic, and there you've got it. There's the limit. So continuous functions are going to make limits for us a lot easier to compute. And fortunately, as I mentioned, most of the functions that we're working with in the class are going to be continuous functions. So they're going to make our work in evaluating limits a lot easier. Well, we're going to look at some more examples here quickly, but they'll go fast because in most cases we're dealing with continuous functions. All right. So let's take a break there and for a few minutes, right? So we'll come back at around 12:35, and we'll look at more of our examples. Okay, are y'all still there? Y'all got very quiet. I was
I'm
talking
here.
a lot. All right. Okay. All right. So, all right. So, take a breather here. Let me pause the record. Okay, guys, I've returned and I have resumed the recording. My screen is very shaky today. Let's see. Okay. All right. So let's look at this one. I'm going to give you all a chance to do this one. So, but this one's very easy. All right. So we want to compute the limit as x approaches 1 of this expression, x squared minus x minus 2 over x plus 1. So if you graph that, you'll get some sort of unusual shaped curve. All right. Going to be kind of a messy to try to graph that, especially if you were graphing by hand. Okay. So trying to compute the limit here by graphing wouldn't really be a very a feasible option. But instead we can compute the limit here pretty rapidly, because this is a rational function. This is what's called a rational function because it's the quotient of two polynomial functions. The top is a quadratic function, and the bottom is this is x plus 1. It's obviously just a linear function, right? So rational functions, which are the quotient of polynomial functions, they're going to be continuous for every number that's in the domain. Now, not every number is in the domain of this function, because notice that if you substitute -1 for x, the denominator will turn out to be 0. So -1 is not in the domain of this function. So that means this function is not continuous at -1, because -1 is not in the domain, right? That's pretty obvious. However, the number 1 is in the domain, okay? 1 is in the domain of this function, right? And so computing the limit here as x approaches 1 should be easy, right? Because this is because this x squared minus x minus 2 over x plus 1 is a continuous function at x equals 1. Okay. All right. So with that in mind, can y'all calculate the limit for me? Try that. Okay. Are y'all back? Is anyone there?
Yeah, I'm here.
Okay. So, all right. Correct. Okay. So calculate that limit there quickly for me.
So negative
Oh,
one.
Saad. All right. So Saad already answered on the chat there. He says it's -1. Okay. So how did you get -1, Saad? Saad, what did you do there to get that limit as -1? Yeah, you just plugged 1 in for x, right? Sure, right. Okay. So indeed, that's all you have to do here, right? Because this expression, this function is continuous at x equals 1, right? That means then that the limit value at x equals 1 and the function value at x equals 1 have to be the same. So you just have to calculate the function value at x equal 1, and that's going to be the limit value, right? So Saad just plugged in 1 for x and did that easy arithmetic, and it just turned out to be -1, right? Okay, so no fancy graphing or anything, right? To calculate this limit. None of this business of having to plug in values for x that are close to 1, right? And try to estimate what the limit is going to be. Here we can just do it really quickly just by substitution, right? Okay, and that's just one of the benefits there of having a continuous function. Now, these functions are a little bit more complicated, okay? At least their expressions are. but they're still continuous functions, okay? So the square root of x squared plus 4, that's not quite a polynomial function. X squared plus 4 is a polynomial, but when you take the square root, that's no longer a polynomial function, but still, this is a continuous function. So again, most of the functions that we're dealing with in the class are going to be continuous functions, at least for every number in the domain of the function. And this function certainly includes 0 in its domain, right? You can certainly calculate square root of 0 squared plus 4, right? And so since 0 is in the domain of this, since this value 0 is in the domain of this function, and I told you that this function is continuous everywhere in its domain, that means this limit is also, see, really fast to calculate. Just plug in 0 for x, right? And you'll come up with the square root of 4, which is 2, right? So very easy there to compute that this limit is 2. Same thing here. This is a cube root instead of a square root, but still also continuous. This function actually has as its domain all real numbers. So this one doesn't have as its domain all real numbers because you cannot take square root of a negative number. So the domain of this function is not all real numbers, but the domain of this function is all real numbers because you can take the cube root of positive and negative numbers. And so, so this is when you graph this, you're going to get a curve that extends all the way across the x-axis, and it's going to be continuous. That curve is going to be continuous all the way across the x-axis, especially at x equals 3. So again, because this formula is continuous at x equals 3, then it's really easy to evaluate this limit, right? You can evaluate this limit just by plugging 3 in for x. So you get 2 times 3 squared minus 10. So that's what the cube root of 8, which is, that's easy. That's 2 again. All right. So this limit also is just going to be 2. So so the notion of continuity there really greatly simplifies, sometimes almost trivializes, right, the idea of computing limits. Same thing in these examples. All right, these are trig functions are continuous. X is just a linear function, so that is continuous. So this is not quite a trig function. It's not quite a linear function because it's the product of x and cosine of x. But the product of continuous functions is continuous, okay? So here, since you're multiplying the continuous function x times this trig function, and trig functions are continuous, so you're multiplying here 2 continuous functions together to get this formula. That means this formula also is continuous, and its domain also, as it turns out, is going to be everything, all right, all real numbers. So that, of course, includes pi. So again, this limit, easy to calculate. All you have to do is plug pi in for x. So you get pi times the cosine of pi, but you do have to remember what the cosine of pi is. What is the cosine of pi? Somebody remember that? Cosine of 0 is 1. So if you have an angle that's opened up to pi, what's that cosine going to be?
-1.
-1, right. So cosine of pi is -1. So you end up getting minus pi, okay? So if you were to make a graph of x times the cosine of x and look and see where the curve is going as x approaches pi, it turns out the curve is going toward minus pi, okay? Sine of x is continuous because that's another trig function. Now this is sine squared of x, so that's not quite a trig function, but this still is going to be continuous. In fact, its domain is all real numbers, and so this function sine squared of x is continuous for all real numbers. Okay, so if you graph sine squared of x, you're going to get a nice, smooth, unbroken curve all the way across the x-axis. If you plug in 0, then for x to evaluate this limit, you just get sine squared of 0. Sine of 0 is 0. So we have 0 squared here, which is 0. So nice simple limit here again, just 0. Okay. Now, of course, there are some cases, right, where, as we saw last time, right, there are a few instances where we do have to do a little bit more work to evaluate limits, okay? Here are some examples of those, okay? So, for instance, if you want to evaluate this limit, this is the same function that we were thinking about just a moment ago. This is a rational function. So it's continuous everywhere in its domain, but the domain does not include -1. All right. So, so you may be wondering, does this limit even exist since -1 is not in the domain of this function? But actually, this limit does exist. But here it does take a little bit of extra work to determine really what this limit is. And what you can do here is factor. It turns out the numerator factors. This factors as x plus 1 times x minus 2. And when you factor that numerator, then you can see the x plus 1s will divide out. So this limit is really just the limit as x approaches -1 of x minus 2. But that now is just that's just a linear function. And -1 is in the domain of this function. So you can evaluate this limit just by substituting -1 in for x. So you get -1 minus 2, which is -3. So actually this limit does exist, okay? It turns out to be -3. But you can't evaluate this one directly just by substituting -1 for x. You have to do a little bit of extra work there. This next example, similar sort of problem occurs. If you try to evaluate this limit by substituting 4 in for x, you're going to see, of course, you get division by 0, right? So 4 is not in the domain of this function, but I think this limit does exist. We just have to do a little bit of extra work to evaluate this limit, okay? I'm going to save that one, I think, for Thursday. And I think I'll save the rest of my examples for Thursday as well, okay? These are 4 examples of evaluating limits where we have to do a little bit of thinking to evaluate the limits. So I'm going to save those to start off the class with on Thursday, okay? All right, because these are kind of special, examples, special cases. But most limits, because of continuity, we'll be able to evaluate pretty easily just by substituting the limit value for x in the expression or in the function. Okay, so I'm going to stop there today and give you a little bit of a break here before the test comes up. All right, so you can get yourself organized or whatever you want to do before the test starts. All right, and we'll take up these other 4 examples of limits next time when you're you'll already have seen the test, so you won't be anticipating the test so much, and you'll be able to pay a little bit more attention. Do y'all have any questions before we stop for today? Anything else you want to clarify?
Will there be like a signature assignment?
Will there be a signature assignment for this course? No.
Okay.
Yeah, there's only signature assignments for certain courses, and that's in certain semesters. That's a method of assessment for the university. We don't have one. We don't have one for this class. Did you want one for this class?
Oh, no.
No, we just have tests. Okay.
All right.
Just the 3 tests of the final exam and the homework. That's our grade.
My question is,
Mhm.
what exactly are we accomplishing when we do the limit stuff?
Okay, so that's a good question. There are and it's a little bit it seems a little bit vague at this point, but Colin, there are lots of situations in calculus where you have to evaluate limits. So we've only seen really one in this course. That is the limit. We had to evaluate limits to, that's part of the definition of derivative, right? Okay. The formal definition of derivative involves computing a limit. Okay. It's a limit of an average rate of change, right? So that's the only example we've seen of where we have to compute limits, but there are plenty of other opportunities in calculus where you have to compute limits. And so this is just practice with learning how to calculate limits. So that's kind of the purpose of it.
I have a question.
Uh-huh.
So, on the test, when you want us to differentiate, just like the basic differentiation, do you need us to simplify at all? Or because on WebAssign we just differentiate and no simplification at all is needed.
Oh, you don't do any simplification? I think on the test
No.
it says, huh? I
And
think on the
what-
test it says simplify as we have in class.
Yeah.
So that would be your goal, Donna. If you don't hit that, that's not the end of the world. Okay. So and the simplification in class is you kind of want to make your final answer look like the original expression. So if the original expression had radicals in it, then you would want your answer to have radicals in it. If the original expression didn't have negative exponents in it, you'd kind of ideally like to have your answer to not have negative exponents in it.
That makes sense.
But if you think you cannot do the simplification correctly, then don't do it. Okay.
Yeah. Cool.
Right.
Thank you.
That would be my advice. Okay. Yeah, that's a good question. Simplify is an ambiguous term in math. It doesn't have a precise meaning. So it means different things in different contexts. So. Okay, other questions there? Okay, all right. So let's stop. Let me stop the recording.